Hi my dear friends, welcome back to our YouTube channel. This is your ADC Maths. So please see that this is the very interesting video lecture. The topic is one-dimensional wave equation, non-zero initial velocity. So in this case, once the initial velocity is given to the string at initial stages, we may allow the string to vibrate by giving some initial velocity in its equilibrium position. At that time, the displacement function becomes zero. Okay, so how we are going to solve this type of one-dimensional wave equation? By giving some velocity. Initially, the velocity is non-zero. What happened in the displacement function? So, see, this is the problem number 1. If a string of length L, so x equal to 0 to x is equal to L, is initially at rest in its equilibrium position, and each of its points are given by velocity. So, see that velocity dou y by dou t at initially time t equal to 0 is 2c by L into x in 0 less than x less than L by 2, and 2c by L into L minus x in L by 2 less than x less than L. Obtain the displacement function. So initially some velocity is given to the string, and it may allow the string to vibrate from this position, and what will be the displacement function during the subsequent motion of the string. So this is the non-zero initial. Why it is non-zero? Yeah, what's the given data? The given data is velocity. So in this case, we may allow the string by giving some velocity. So once it is velocity means, what are the boundary conditions? Let us see that one by one. So as we know that the one-dimensional wave equation is dou squared y by dou t squared is equal to a squared into dou squared y by dou x squared. This is my equation number 1. As already you know that what is a squared? A squared is tension of the string by mass of the string per unit length. And when we solve this equation, we get the required displacement function y of x. Now, from the given problem, in this case, this comes under non-zero initial velocity. So from this problem, we have the following boundary conditions. What are the boundary conditions? The first boundary condition for the left end x equal to 0, it is fixed. So there is no displacement taken place at this point for all the time t equal to 0. And the second condition for the right end at x equal to L. So at x equal to L, so we get y of L comma equal to 0 because that point is also fixed. So no displacement at that point. And third one, this time let us see that non-zero initial velocity. So velocity is given. So this time the displacement function is 0. So the third one, initial displacement function is 0. Initial displacement function is 0. That means that y of x comma 0 is equal to 0 in 0 less than x less than L. And the fourth one is velocity. What's the velocity is given now? Dou y by dou t at the time t equal to 0 is equal to, what is that? Something like 2c by L into x in 0 less than x less than L by 2, and 2c by L into L minus x in L by 2 less than x and less than L. Now I am going to apply the conditions one by one. So as already we know that what is the correct solution? The correct solution of the one-dimensional wave equation is y of x comma t is equal to a cos px plus b sin px into c cos pat plus d sin pat. So this is the equation number 2. Let us apply the condition number 1. So using the condition number 1, using the boundary condition number 1 in number 2, by putting x equal to 0, we get. So by putting x equal to 0, we get cos 0 is 1, sin 0 is 0. So we get A. There is no x term here, so this is simply like c cos PAT plus d sin PAT is equal to 0 because the left hand is fixed, isn't it? The left hand is fixed. The point is fixed here, so there is no displacement taken at this point because it is fixed. And even please kindly go and watch the zero initial velocity problem number 1 video. The same first two boundary conditions already have discussed the same thing here. So either a equal to 0 or c cos PAT plus d sin PAT is equal to 0. Isn't it? Now this is not equal to 0 since for all the time t, even though by putting t equal to 0, minimum case t equal to 0, we get only it is sin 0 0, cos 0 becomes we get only c equal to 0. But when we get this is 0, both c and d 0. But both c and d become 0, what happened? The entire solution becomes 0. We can get 0 solution. But there is a contradiction to the given data because it may have some kind of non-zero initial velocity. So there is have some non-zero velocity means there is some non-zero displacement as well. So that is my requirement. What is the velocity? That's what is the displacement during the subsequent motion. So this case is not equal to 0 is confirmed. So what is the balance one? The balance one is a equal to 0. So once we substitute a equal to 0, we substitute a equal to 0 in the correct solution number 2. We get y of x comma t is equal to b into sin px into c cos PAT plus d sin PAT plus d sin PAT. So this is my equation number 3. So I substitute the first boundary condition, I found that a equal to 0. What about the second boundary condition? When x equal to L, there is no displacement because this point is also fixed. This point is also fixed, so there is no displacement taken place at this point number 2. That is x equal to L. So shall we apply the condition number 2 now? So if I substitute the condition number 2, yes, now using condition number 2 in the equation number 3 by putting x is equal to L, we get, so b is already there, x equal to L, we get sin PL and c cos PAT plus d sin PAT. So once again, at this point there is no displacement. At this point there is no displacement, so it's equal to 0. So this means that either b equal to 0 or sin PL is equal to 0. It's a product of b into sin PL into c cos PAT plus d sin PAT is equal to 0. C cos PAT plus d sin PAT equal to 0. So I think already I have explained here, this is not equal to 0 for all the time t is not equal to 0. And what about the first one? Suppose b is 0, what happened? Sir, already a 0 now. Now b is also 0. We get the entire thing is 0. We get the entire thing is 0. So this is the contradiction because entire thing is 0. Then how we will get the velocity? Isn't it? So b is not equal to 0. Since already a 0, we can get trivial solution. Right, sir? So please just go and watch the one-dimensional wave with zero velocity type problem number 1. The same concept. So what is the balance? The balance is sin PL equal to 0. This is equal to sin n pi. So by this way we get P equal to n pi by L. So once we get P equal to n pi by L, substitute P equal to n pi by L in the equation number 3 because equation number 3 is the latest one. Right, sir? In the updated one. In the equation number 3, we have, so when we substitute P equal to n pi by L, we get this y of x comma t is equal to b into sin of p is equal to n pi by L. So n pi x by L. And what about the rest of the c cos n pi a t by L plus d sin n pi a t by L. So this is the latest updated version of the displacement function equation number 4. So I applied the first boundary condition, I found that a equal to 0. Second one we get p equal to n pi by L. Now the third one is initial displacement is 0. That means when time t equal to 0, the displacement is 0. So can we apply the third boundary condition here? So using boundary condition number 3 in equation number 4 by putting t equal to 0 we get. So first two boundary conditions for x. First one x equal to 0, second one for x equal to L. Now the third and fourth one for time factor t equal to 0. Now by putting t equal to 0, number 4, we get it is b into sin n pi x by L, right? So there is no t term, so it is constant. By putting t equal to 0, cos 0 is 1, sin 0 is 0, so we get it is c equal to 0 because displacement is 0 at t equal to 0. Displacement is 0 at t equal to 0. So now this means that either b equal to 0 or sin n pi x by L is equal to 0 or c equal to 0. As I already told you that c not equal to 0, b not equal to 0 because already a is 0. So if already a is 0, now b is also 0, then we get the complete thing is 0. Now, what about sin n pi x by L? This is also not equal to 0. Why? Because it is lies between 0 and the L. If x equal to 0, sin 0 0. That is true because of the left hand is already fixed. So there is no displacement. And the right hand is x equal to L. So there is also sin n pi 0. That is also 0 because of this is also fixed. So that is we have discussed separately as a boundary condition number 1 as x equal to 0 and x is equal to L. So there is no doubt. So between the 0 and L means when we choose x equal to L by 2, for example, we get sin n pi by 2. What is sin n pi by 2 value? When n equal to 0, sin 0, 0. When n equal to 1, sin pi by 2 plus 1. N equal to 2, sin 2 into pi by 2, sin pi is 0. When n equal to 3, we get sin 3 pi by 2 minus 1. So from this, what happened? This is not at all 0 generally. So this is not equal to 0. So which one is 0 now? C equal to 0. Now substitute C is equal to 0. So only one possibility in the fourth equation. We may get y of x comma t is equal to, what is it? B into sin n pi x by L. Now this time C is 0. So this time C is 0. So C into 0 is something 0. So we get d sin b at sin n pi at by L. Now I can combine this b and d. I can combine this b and d as the constant. So what have we get? When I combine this, we get this. I can name this Cn. So Cn is if we combine b and d. So Cn sin n pi x by L into sin n pi at by L. Right? If n equal to 0, what happens? Sin 0, 0. So we don't consider n equal to 0. N equal to 1, n equal to 2, n equal to 3, n equal to 4, which may give the different possible solutions of the required displacement function. By combining all possible solutions, we may get the most general solution. So the y of x comma t is equal to sigma n equal to 1 to infinity Cn sin n pi x by L into sin n pi at by L. So this is the most general solution for non-zero initial velocity problems. So up to the star equations, most probably is fixed for all the problems. Now in this problem, the fourth boundary condition still I have. What's the fourth boundary condition? The velocity is given at the time t equal to 0. So can we use this? We may get the remaining constant Cn. So let us apply the fourth boundary condition in the most general solution. I am getting the required Cn, that is the required displacement function. Finally, using condition number 4 in the most general solution by putting t equal to 0, we get what we get, sir? What we get? We get by putting t equal to 0, sigma n is equal to 1 to infinity capital Cn sin n pi x by L. I think so. This is only the displacement function. I need the velocity. So before going to apply the fourth boundary condition, better we can differentiate the star equation with respect to t. So differentiate star equation partially with respect to t, partially with respect to t. What we will get? We will get dou y by dou t. Is right? Dou y by dou t is equal to, with respect to t alone, so x term is cancelled. So Cn sin n pi x by L. What about the sin n pi at by L differentiation? Cos n pi a t by L into the constant n pi a by L. Understand? So differentiate process because of velocity. Velocity means rate of change of displacement with respect to time t. So this is the displacement only. So differentiate. Now apply the condition number 4 in this step. We get using condition number 4 in the above equation by putting t equal to 0. We get sigma n equal to 1 to infinity Cn into sin n pi x by L. What about cos 0? Cos 0 is 1. So n pi a by L. So I can combine with the Cn n pi a by L is equal to, what is given now? The given is 2c by L into x in 0 less than x less than L by 2, 2c by L into L minus x in L by 2 less than x less than L. So this is the my given velocity f of x. Now how to get the Cn? I have seen that the left hand side is looks like the half-range sine series. So can we express the f of x as half-range sine series? We may get the required Cn. So by using the half-range sine series, the left hand side becomes sigma n equal to 1 to infinity Cn n pi a by L into sin n pi x by L is equal to, what's half-range sine series formula? Sigma n equal to 1 to infinity small bn into sin n pi x by L. Right? Now equating like coefficients on both sides, so sigma sin n pi x by L. So what's up? Small bn is equal to this one. So Cn into n pi a by L is equal to small bn. So bn is equal to Cn is equal to bn into L by n pi a. So this is the Cn value. So this is my equation number hash. So after putting the Cn value, substitute the Cn in the star equation. How to get the Cn value? That's the question. How to get the Cn equation? Yeah, as I told you that to find the half-range sine series, now this is equal to bn into L by n by a. What's the bn formula in the half-range sine series? Yeah, 2 by L. The same concept. Yes, you are correct. 2 by L integral 0 to L f of x sin n pi x by dA. So can we go for the formula? Bn is equal to 2 by L integral 0 to L f of x sin n pi x by L into dx. Now the function f of x is given 0 to L by 2 and L by 2 to L. So can we go for the Bernoulli formula? Yes, right, you are correct. You go for the Bernoulli formula. So let us apply the Bernoulli formula. You will get the Bn value. So what is the Bn now? Bn is equal to 2 by L. The function is defined in two subinterval 0 to L by 2. The function is 2c by L into x sin n pi x by L into dx. Now the second interval part L by 2 to L. L by 2 to L is 2c by L into L minus x. 2c by L into L minus x into sin n pi x by L into dx. So this is the formula for the Bn. I found that 2c by L, 2c by is constant term. So let us take the 2c by L outside. So 2 by L, 2c by L is taken outside. For the balance, this is the balance one x. So I use the Bernoulli formula. So x into sin n pi x by L integration is minus cos n pi x by L by n pi by L. Minus formula minus x with respect to x1. This becomes minus sin n pi x by L by n pi by L to the whole square. With the limit x is equal to 0 to x is equal to L by 2 plus the second one L minus x differentiation is, so it's a u, this is v. So by using the Bernoulli formula, L minus x, sin becomes minus cos n pi x by L by n pi by L. Right? Minus formula minus L minus x differentiation is minus 1 and this becomes minus as it is retained. Cos becomes sin n pi x by L by n pi by L whole square with the limit x is equal to L by 2 to x is equal to L. Right, sir? So can we apply the limits? Yeah. Once we apply the limit for this, we get this 4c by L square first of all. By putting x equal to L by 2, we get here this minus L by 2 into the reciprocal L by n pi. Now cos n pi by 2. Is right? Minus plus L by n pi to the 4 square sin n pi by 2. By putting x equal to L by 2, we get sin n pi by 2. For the lower limit, this is 0 and then 0, sin 0, 0. So we leave it. Similarly, in the second term, by putting x equal to L minus L 0, by putting x equal to L will cancel, sin n pi 0. So this upper limit is 0 minus the lower limit. So minus of minus becomes plus. Putting x equal to L by 2, L minus L by 2 is plus L by 2. The reciprocal L by n pi. By putting x equal to L by 2, we get cos n pi by 2. Yeah, minus of minus plus, plus minus minus, but upper limit minus one lower limit, so this becomes once again plus the reciprocal L by n pi to the 4 square. By putting x equal to L by 2, we get sin n pi by 2. Right? Now, this is a minus term, so plus term will cancel. So the balance is, so 1 plus 1, 2 times, so 2 into 4, 8. So this we get is equal to 4c by L square 2 times L square by n square pi square sin n pi by 2. Is right? Now cancelling the L square, we get 4c by L square equal to that is 8c by n square pi square into sin n pi by 2. So this is my Bn value, but I need the Cn value only in the most general solution. So can we use this Bn value in the hash equation? Using Bn value in the hash equation. What's hash equation? This one. So what's the Cn? Cn is equal to Bn into L by n pi. So Bn is now this much multiplied by L by n pi a. Along with this we get 8c L by n into n square is n cube, pi into pi square is pi cube into a of sin n pi by 2. So this is my capital Cn value. Now use this capital Cn value in the most general solution. We will get what we will get, sir, by putting Cn value sigma n equal to 1 to infinity. Cn value is 8cl by n cube pi cube a of sin n pi by 2. Right? Now sin n pi x by L, sin n pi at by L, sin n pi at by L. So this is my required displacement function. Is the required displacement function under the non-zero initial velocity. Under the non-zero initial velocity, both the terms are sine. One for x, one for t. One for x, one for t. So this is the first problem under the non-zero initial velocity. So thank you so much for watching our videos. And please support us, support our YouTube channel ADC Maths. Thank you so much.